In this session, we are going to extend our discussion on minimum spanning trees. So last time we had looked at the Kruskal's algorithm and we looked at how to derive a minimum spanning tree from a graph using the Kruskal's algorithm. So let's recall and do a quick recap of our understanding on minimum spanning tree. So a spanning tree is simply a tree that's cut out of a graph, right? So you could have many different spanning trees in a graph, and we are looking to find the minimum spanning tree so that one can then visit all those vertices in a minimum cost. So we are given with a graph which is an undirected graph G, and then we are given with the set of vertices V and the set of edges E, and we like to find out the minimum spanning tree, which is simply a subset of that graph G, such that all the vertices remain connected. That's the important property there. Second property is the sum of weights or as minimum as possible. So in this session, we will look at the Prim's algorithm, which is again another greedy algorithm that works for a undirected graph to find the MST. So we are given with a graph G in this example. And here, unlike the Kruskal's algorithm, where we had chosen the start vertex to be the one that is the minimum vertex when it comes to us doing all the sorting of edges in increasing order. So we found the minimum edge and then we started from there. Unlike Kruskal's algorithm, Prim's algorithm can start from any arbitrary vertex. So it can start from 0, 1, 2, 3, or 4 in this particular example. But here we are simply choosing 0 as the start vertex, but one can choose any vertex for that matter, right? And then we are maintaining two lists here. One is the E prime. E prime is simply a subset of the capital E, which is the edge set, right? So E prime is simply going to be a subset of all the edges that we have in the graph. And T here is going to include all the edges in our minimum spanning tree, right? So both of them are initially set to empty, but then later we will build on that. So first thing first is we choose 0 as the start vertex, and then we look at all the vertices that are adjacent to that 0, and basically we choose all the incident edges, right? So incident edges or the edges that comes out from that particular vertex 0 in this case, right? So again, you could see from 0 we have edge 0, 1 that's incident to 0. Then we have 0, 3 that's incident as well, and then 0, 4, right? So we add all those edges that are incident of that vertex 0 to this E prime, and then we choose the minimum one from that list there, right? So we have 0, 1, 0, 3, and 0, 4, and 0, 1 is the minimum one, which is the edge weight 3, and then we add that to our T list, right? So we are saying that we are taking the edge between 0 and 1, and we are visiting 1 here, right? So now as a next step, we take 1 and then we find all the incident edges for 1 and we add it to that list, right? And keep in mind, once you have chosen an edge, we need to remove that from that E prime, right? So we removed that from E prime. So the second step here is to find all the edges that are incident to 1, the vertex 1, I mean. So you have an edge 1, 2, and 1, 3, right? If you look at the original graph, we had two edges incident to one. So we are adding those two edges to that E prime. And then we choose the minimum one now from that entire list. Keep in mind, every time we need to select the minimum one from that entire list. So now it apparently the one that we will choose is 1, 2. So we remove that and we add it to T prime. And now we had visited the vertex 2, and this is from vertex 1, right? So now again we will go to the vertex 2 now and look at all the incident vertices, right? So incident edges, I should say, and we add them. But keep in mind, we could only add to E prime if there is no cycle. Okay, so here you can see we have 2, 3, and 2, 3 is added right here, right? And then again we are going to look at that entire list, and we are going to choose 2, 3 is the best one, right? So we are going to go and add 2, 3. So let's go ahead and look at the original graph for a second here. I'd like to go back to the original graph. So here you could see from 2, there were 2 incident vertices, right? Incident edges, I mean. So you have 2, 1 and 2, 3, but we never added 2, 1 because 2, 1 is already added to that list, right? So we don't add something again, we just add the unique edges, right? So here you can see that 2, 1 we had already scratched out, so we don't need to add that, and we are adding 2, 3. So once we are done with 3 now, we had visited 3, and then we now shift our focus to 3, and we find all the incident vertices for 3, and apparently there is 3, 4 coming in. So we add that, and then we find the minimum one from that entire list. And keep in mind, every time you add something to the T list, you should remove that, right? So now we will add 3, 4, so we will remove 3, 4, and we added 3, 4 to the T list. So the next one in the sequence, the minimum one, apparently we will choose the 1, 3, right? So 1, 3 was the edge, which is the next minimum one. But keep in mind, 1, 3, we cannot add it because it creates a cycle, right? If we add 1, 3, then it will create a small cycle right here. We don't want to do that. If you remember, the important property of MST is that a tree cannot have a cycle, right? So we don't add 1, 3, we simply remove that from that E prime, right? So 1, 3 will be removed from E prime. And the next one that we have is 0, 3, right? Again, we are going to look at our list in that E prime, and we find the minimum one. 0, 3 is the next one. And again, you can see if we add 0, 3 to T to our MST, then it will create a cycle. So we don't want to do that, right? So we never add that. And then we are going to remove that from the E prime. And finally, we have 0, 4. And again, same problem. If we add 0, 4, we create a cycle. You see? We don't want to do that. So we never add 0, 4 to T, and we simply remove that. Right? So the algorithm runs all the way through till this E prime gets empty. Right? So when E prime is empty, that means then we had visited all the vertices, and we had created the MST. And also keep in mind, this T here is of size V minus 1, right? So where that V here is simply the number of vertices. So here we have 1, 2, 3, 4, 5 vertices. So your T will have only 4 elements. That's 5 minus 1 is 4. So it will have only 4 edges. Basically, the size of T will be 4. So this is our final MST, and you should compare this with our Kruskal's example that we have seen in our last session. It's basically the same graph and same MST, right? It produces the same MST, except that we use a different algorithm this time, right? And also keep in mind, the total count is what matters here, right? So we need to find out the total count. So 3, 1, and then you have 2 and 3. So that's total 9, right? So the total cost for this MST will be 9, right? So let's look at the formal algorithm. Again, we are given with the graph G, which is undirected, and we are trying to find the output minimum spanning tree T, which is an element of capital E, right? So first thing, we initialize T, then we start with an arbitrary vertex U, which is element of the V, and then we add all vertices V that are incident to U in E prime to E prime, right? So we start with adding all the incident edges to E prime basically, and then we pick one such edge which has the minimum weight in E prime, and we check if it creates a cycle. We simply remove it. If it doesn't create a cycle, then we add that edge to T, and then we remove that from E prime, right? So this while loop will run, and this while loop would run a maximum of big O of V plus E times, right? So it runs for big O of V plus E for all the vertices V and all the edges E, right? So that's how many times it would run. Because keep in mind, for each vertex, we are going to look at all its edges, right? And then again, we are going to look at a vertex. We look at all its edges. Again, we look at another vertex, look at all its edges. Now, in total, we are going to look at V plus E edges, right? In total, we look at V plus E, big O of V plus E when it comes to the total exploration, right? But keep in mind, we are also doing a picking here, right? So picking the minimum one. So if you would recall, we used the heap sort to find the minimum one, right? So we can always do a heapify process, and the heapify was done in big O of log n, right? If you would recall from our earlier lesson, when we talked about heap sort, at any point of time in a tree, we could find the minimum one in big O of log n, right? So to construct the tree, it will take big O of log n so that we can find the minimum one in big O of log n, right? So inside that while loop, the picking procedure runs for log V, right? So we have total of V vertices, so it's going to run for log V, right? So that's the time complexity here. Again, V plus E is the total exploration for the while loop, and then picking takes log V. And again, we are assuming that we are using a heap to implement that picking procedure, right? If we implement the picking using the heap, then it will take log V, right? Because there are V vertices, and hence it will take log V. So that's the time complexity analysis. And again, we will take up one exercise here for today to practice this Prim's algorithm. Again, we are taking the same graph G, which we did last time. Last time we did the Kruskal's algorithm. Now we are going to do the same thing with the Prim's algorithm. And I like to see in your solution to include the edges E and T at every step so that we can compare that with the Kruskal's algorithm. But the final output, I should say, would still be the same, right? The final output should match. That's our goal as well. Our goal is to match Kruskal's, right? So we should match Kruskal's algorithm for the final output. But your edge set E and T would have some changes, right? So for example, the order of edges added in T will be different from Kruskal's, right? Okay, so the next step for us is on Friday and Monday next week. We are going to look at least one, if not two, string algorithms, right? So we will look at a couple of string algorithms to wrap up this semester here, right? In the Sedgwick 4.3, if you have not done so already, I recommend you to do the reading assignment. If there are any questions, feel free to ask, okay? All right. Well, thanks for listening and watching this video.